Hello. In this video, we'll talk about polynomial functions. It's an introduction to polynomial functions. Well, we had been using polynomial functions for a long time without really getting introduced to them. Let's recall some of them today. Okay. Some of the most interesting functions will be dealt. Let's start with fx equals to 0. Well, this is called a zero function. We normally use it, but it is not really understood so well. When I ask my students about it, what will they do? If I say plot this function fx equals to 0 on the coordinate system, what are they going to do? Most of them just put a point there at origin, fx equals to 0. Well, this is just a point on the function fx equals to 0. What is this function doing? Here, whatever input comes into the function gets out as a 0. This function is valid for each and every value of x. That is, x belongs to real numbers. So for every real value of x, we get what as an output? 0. So this is a set of points on our x-axis. You see that? So fx equals to 0 really represents the x-axis. Okay, so remember that part. It is a function which represents x-axis. Now let's talk about another function which we call as constant function. Let's name it k. Kx equals to minus 5. That means what? This means for each and every value of x, the output is minus 5. Let us say this horizontal line represents kx equals to minus 5. Okay, it extends from negative infinity to positive infinity. The domain is all real numbers. It never intersects x-axis. It is parallel to it, and therefore it does not have any x-intercept. Right? Let's consider a linear function. Lines. We have been dealing with them for a number of years now. Let me represent line with L. So let's say Lx equals to, let me draw a line first. Let's say this is our line. Okay, and let's assume this point is 3 and this point is let's say 1.5. So this point, so rise over run is the slope. You can see that the line goes down, so the slope is negative. Now it goes down here, rises minus half, 1.5, and the run is 3. Therefore, the slope is negative half. So we can write the equation of this line as negative half x plus y-intercept, which seems to be half. Okay, let me write this as half. So that's the equation of this particular line. Now, let's consider another function, a quadratic function. It looks like a parabola, correct? Let me draw one. Let's say this is our quadratic function. Now, this quadratic function is here with y-intercept of 2 and x-intercepts are 1, 2, 3, close to 4, right? Minus 4 here. 1, 2, 3, 4, 4, close to 4, plus 4 plus on this side. So it has got 2 roots, 2 x-intercepts, and it opens downwards. Let me call this quadratic function by the letter q, and let's say qx is, we can give it an equation as, let me just approximately give it as 2 times x, the 2 has to be negative, correct? Negative because it is opening downwards. X squared plus, let's say 2. Okay. It really does not represent this, but similar to this, it will represent a family of this function. Okay. If you want to do this, then it should be close to, let's say 9. Then it will be very close to our graph. Let's write this. Minus 2x squared plus 9 as our quadratic function representing this parabola. Now let me draw a cubic function. cubic functions look like this. Let's name it C, cubic x, and let's say the equation of this function is x cubed plus x squared minus 12x. Okay. We can draw more functions like this, and let me just take a vague function. Let's say we have some function like this. Let me use a blue ink for this. Let's say the graph is like this. It turns here, it turns again, goes like this, goes like this, and then goes like this. Let's say this is a smooth curve, right? Is a function with much higher degree than 3. Approximately, let me call this polynomial function by the name P. We could write the equation of this polynomial function using the x-intercepts. We will actually see in the next video how to write down the equation of a polynomial function. But for the time being, let me just use 1, 2, 3, 4, 5 these x-intercepts and figure out what the equation is. Let's say it's approximately 5 where it turns. So one root is at, let's say, minus 5. In that case, this will give us a factor of x plus 5 square. Square because it turns. Here also it turns. Let's say this point is 1. So this will be x plus 1 square. And then it goes straight at 1. Let's say this is x minus 1. And here also it goes straight. So it is 1, 2, 3, 4, 5. Let's say this point is 5. Let me say this is x minus 5. The y value will give us some value for a. For the time being, let's write this to be, let's say, 1 over 100. Okay. Now this is kind of a bigger polynomial, complicated function, which you will be dealing with quite often. Right. Let's see similarities between all this. Well, one similarity is obvious. All are continuous functions. Here the domain is x belongs to real number. Correct? So first thing we saw here is they are continuous functions. Correct? Second, we see, do you see any sharp edges or corners? No. So no sharp edges. So there is, no corners, no cusp. Now what is the cusp and what is the corner? Like you see this absolute function, this is your corner. And cusp is when you do some square root functions, you get functions like this. These are kind of cusp, okay? So we don't have any of these. Therefore, if you see a function which is kind of like this with a break here and then starting like this and going like this, then this will not represent a polynomial function because it has got breaks, it has a corner, things like that. Any one of those things will disqualify it for being a representative of a polynomial function. Okay. Now we see common characteristics here are all are continuous. That means x belongs to real numbers. Okay. That's the domain. And no corners and no cusp. Now looking back into these equations, what we find is they have one variable. The variable I've shown here is x. Second, these x can have exponents, and these exponents are positive. Now, these exponents actually give you the degree of our polynomial. The highest degree is the degree of the polynomial. For example, the highest exponent here is 3, so the degree is 3. It's a cubic function. In this case, the highest degree is 2. So the degree of the whole polynomial is 2. It's a quadratic function. Here, the degree is 1, x to the power of 1. It's a linear function. And here, what is the degree? The degree is 0. You can call this as like minus 5 x to the power of 0. So the degree is 0. And here, therefore, the degree is 0. This number associated with the highest degree variable is called the leading coefficient. In this case, the leading coefficient is minus half. In this case, it is minus 2. And in this case, it is just a value 1. Let's write down another function. I'm calling it m. Let's say I write like this: 2x squared minus 3x to the power of 5 plus 7x to the power of 9 minus x plus 4. Did you see? I wrote a function where the degrees are not written in order. Well, equation can be given like this. It is not wrong, it is correct. Generally, when you write an equation, you should write the highest degree first and then in decreasing order. That's the best way to do it. But anyway, in the test, you may find polynomial functions represented by this. Now, knowing that all these are polynomials, let's try to give them one particular equation which could contain all of them in one. So all these polynomials can be represented by this complicated, huge equation. Polynomial px is equal to an x to the power of n plus an minus 1 x to the power of n minus 1, so on. With decreasing powers, it goes on. a2 x squared plus a1 x plus a0. So in general, this could be a polynomial. As you saw that here, do you see that this is a constant? That means x was 0, right? When x is 0, then this becomes a constant, a0, right? Well, in all this equation, you remember line, what does this represent? This constant represents y-intercept. That's an important thing to understand and remember. a0 represents y-intercept. Okay? Y-intercept. Why? Because at x equals to 0, the value of polynomial is a0, the y-intercept. Okay? Now, let's look into some other things. Here we have one variable x. So most of the polynomials which we are going to deal with will be just x, one variable. N. What does n represents? N gives us degree of polynomial. N will be the highest value in this equation, and n gives us degree of polynomial. It is not necessary that the first term will have the highest degree. Somebody can write equation like this. You have to search for a term with highest degree. For example, in the equation mx, what is the degree? The degree is 9. Okay? Because 9 is the highest degree of any term. And an, a's in general are all constants, right? And they also belong to set of real numbers, but they are constant values. The only variable in this equation is x. An plays a very important role in the end behavior of a function. See, if x value is very large, then that large to the power of a large number will be extremely large value. Therefore, this will dominate the characteristics of the polynomial. So, end behavior is decided by this leading term. Let me first write that. An x to the power of n is called the leading term. And what is an? An is coefficient of, or you can say leading coefficient. Okay, that's better. So we say coefficient of leading term. A better word would have been leading coefficient. Okay. Now, a and xn is the leading term. As you can see, in general, what are all these? These are all different terms combined together to give us a polynomial. In general, each term is like a power function. You see, each term is a power function. X to the power of something, 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 here also x to the power of something, which is 0. So, what is a polynomial? Another way of defining a polynomial is, it is sum of power functions. Okay, sum of power functions. Now, what is a power function? Power function is a x to the power of n. This is a power function, right? Now, a can have different values and there are many terms, right? So n can change from 0 to any number. Okay, so sum of power functions is a polynomial. Now, knowing that these are polynomials, it is a good place to think about what are not polynomials. Can you give me examples? Not polynomials. Let's write some equations which are not polynomials. Okay. For example, let's write y equals to x to the power of minus 3 plus 2 x to the power of minus 2 minus 3 x to the power of minus 1 plus x plus 5. Is this a polynomial? No, it is not a polynomial. Why? Because the values of n are negative. But what we said was n should be what? N should be always non-negative integer. Okay? So in a polynomial characteristics, we find that n, which is the degree, let me put here, n should be non-negative integer. Non-negative integer means like 0, 1, 2, a whole number. Okay? We cannot say n is positive integer. In that case, we don't know whether it includes 0 or not, right? So let's be very specific. Non-negative. That means it includes 0, 1, 2, 3, 4, a set of whole numbers. Correct? So this is not a polynomial since n, the exponent, is negative. Similarly, if I write y equals to square root x plus 1, this is also not a polynomial. Here, what is the exponent? 2 over 1 over 2. Okay? So this is not a polynomial. Or if we write y equals to x plus 1 over x, here, this is another way of saying x to the power of minus 1. This is also not a polynomial. Or we write y equals to 2x plus 1 over 3x minus 1. This is a rational function. This effectively is degree negative exponent, right? So this cannot be right. Or we write a function like y equals to sine square x minus sine x plus 1. Well, a's are all constants. They are not sine, log or exponential functions. So these are set of values, set of equations which do not belong to polynomial functions. Okay? It is very important for us when we look at a polynomial to find out what is the value of leading coefficient and what is the degree of a polynomial. Now, if an equation is given, straightforward equation, just as we saw mx, I'm writing another equation here. Let's say if an equation is given as 2x to the power of 7 minus 3x cubed plus 10x to the power of 12 plus 5x minus 1. Then you have to look into the equation for the highest degree. Now here, this term has got the highest degree. Therefore, this term is the leading term. And in this leading term, what is 10? 10 is the leading coefficient, plus 10. And What is the degree of this polynomial? Degree of the polynomial is 12. Let me give you another kind of equation. Let us say px is equals to minus 2 times x square plus 1 times x minus 3. Now, if I give you in factored form, how will you find the leading term? Well, you don't really have to do distributive law, expand it fully. What you can do is multiply to get the degree, highest degree, okay? So when you do that, you can see from here, when you multiply these terms, you get your leading term. And in this case, x times x is x cubed times minus 2. So it becomes minus 2x cubed. Therefore, what is the degree of this function? The degree of this function is 3. It's a cubic function. And the leading coefficient is minus 2. Okay? So I hope you understand how to find the leading coefficient, how to identify the leading term, and check whether it is a polynomial or not. Okay? So we have understood all this. Now in the next video, I will tell you or explain you the power function, ax to the power of n. Once we understand power functions, then we will see the characteristics of our polynomials, since polynomial is just sum of power functions. Okay, so that would be a good point to discuss the characteristics. For now, remember that polynomials are continuous functions which do not have any cusp or corner. They can be represented by an equation like a n x to the power of n plus a n minus 1 x to the power of n minus 1 and so on, where a's are constants which can have real values, n's, exponents, can have only whole numbers as their values. Okay? Thank you.